So welcome again. This video will explain the different aspects of fused deposition modeling. What do you mean by wire additive manufacturing? Means we are using the raw material in the form of a wire. That's why this is called a wire additive manufacturing. So one type of this additive manufacturing is fused deposition modeling or FDM. This is the most commonly method 3D printing uh, is adopted by uh, educational peoples, hobbyists, in research organizations, so and so. The other name of this technique is fused filament fabrication, FFF. So FDM and FFF are same. So in the screen, you can see the image of a fused deposition modeling setup. So I will start from the top. You can see support filament spool and spool of filament. So there are two materials. One is for supporting the part we are going to print, and the next is the material to print the part. And this material will enter into the extrusion head, and then with that extrusion head, the solid material will convert it into liquid form, and the liquid material will come through the printing nozzle, and there is a small orifice at the end of the nozzle. So from the opening of the printing nozzle, the material will come out in the form of liquid, and the material will add into the substrate or the platform, build a platform, so that we will get the 3D physical model. So this represents the printed part, and when one layer is completed, then the build platform will move in the Z direction, bottom direction, with the layer thickness, so that the printer will add the next layer of material. So from this image, it is very clear that uh, the basic working principle of the fused filament fabrication or fused deposition modeling. So we will explore some different images. Yeah, this one is again same concept but different image. To understand the idea clear, we can use some different images so that we can easily understand the concept very clearly. Yeah, again, this is here. I will start from the right side. We can see two different colors. So one color represents the support material. This is for supports the structure, and the next color represents the model material spool. So this material is used for printing the part. So here in the image we can see part and supports. So this is my part required. This is my final fabricated part, and here there are two openings. So in that opening, I am providing support structures. Otherwise, what will happen when I am adding material here? There is no material here, or there is no support here because of the gravity. The material I'm going to add will come into the bottom portion, so that I'm not getting the actual shape. So to avoid that situation, we are providing support structures here. So this is the support structure, and this is the support structure. So to print a support structure, we need support material. So this orange color is representing the support material, and the other color is representing the uh, part material. And then this material will enter into the extrusion nozzle. So this is the extrusion nozzle, or this is also known as liquefier, and this liquefier moves in both X and Y directions. So both the support material and the model material will enter into the liquefier, and inside the liquefier the solid raw material, the wire formed solid raw material will convert into liquid form, and that liquid raw material will come into the platform through the small orifice. In this image, we can see the build platform. Actually, the part is printed on the build platform, and the movement of the build platform will be in the Z direction. So this platform can move both plus Z and minus Z. This is the Z direction. And in the case in the liquefier, this liquefier is moving in both X and Y directions. So this is another image representing the basic working of fused deposition modeling. So we will take another figure. Yeah, this is another figure representing the same concept. Here there is no support material. Here is only one the only one material to print the part. Okay, and this is the plastic filament, and this plastic filament will enter into the this is called a pinch roller mechanism, and this roller will roll, and this material will enter into this space, and the roller is rolling so that the material will enter into the liquefier. This is the liquefier, and inside the liquefier the material will convert into from solid into liquid, and that layer will add here so that we will get the part. So here this fabricating part is our final 3D printed object. And yeah, this is I can say this is called extrusion head, and the movement of this extrusion head is both X and X and Y movement, and this base plate or this fabricating part, this part is having the Z movement, plus Z and minus Z. So here in the figure we can see the axis representation. This represents Y and this represents X, and this upward and downward motion represents the Z movement. Again, this is another figure to represent the working of fused deposition modeling. Yeah, this one is again another figure, but the idea is similar. We can see, I will start from the left side. Here you can see two materials. One is build material spool, and another one is the support material spool. And this is for building the part, and the dark blue is representing the part color, whereas the light blue is representing the support structure. So in the part we can see the dark blue is representing the part, and the light blue is representing the support structure. Okay, so that we can easily remove the support structure during the post processing. So this material will enter into the extrusion head. This is the extrusion head. So the zoomed the zoom in view of the extrusion head is displayed here. This is the zoom in view of the extrusion head. So here you can see two materials. One is support material and another one is the build material. And this is called a pinch roller mechanism or drive wheels. So first the material will enter into the drive wheels or the pinch roller mechanism. So through the pinch roller mechanism, it will enter into the liquefier. This is called a liquefier. Inside the liquefier, the solid wire formed material will convert into liquid form, and through the nozzle, through the extrusion nozzle, the material will come in the form of liquid, and that material will add here so that we will get the final part with the help of the layer by layer additive manufacturing technique. So this is the basic working of the fused deposition modeling. Yeah, we will take another figure. Yeah, again this is again another figure representing the working of fused deposition modeling. This is the model material. This red color is, so this gear represents our final part. Okay, and you can see the color. This is the color of the model material. So this material will come into the pinch roller mechanism, and then from the pinch roller mechanism, this will enter into the a heated extrusion nozzle, and through the extrusion nozzle, the material will come in the form of liquid, and that will add layer by layer so that we will get the final product. And this color represents the support material, and this gear, this overhanging structures, we are supporting the overhanging structures with the help of support material so that we will get the proper shape. Otherwise, because of the gravity, when I am adding the material, I will not get the proper shape because of the gravity, because of the overhanging structure, and because of the gravity, I will not get the proper shape if I am not providing the support structure. So this is again another image showing the working of fused deposition modeling. Yeah, this one is again same. The central line, this line represents the filament. So this is our raw material. This will enter into the pinch roller mechanism. So through the pinch roller mechanism, the material will enter into the liquefier or material melting heating block. We can call this as material melting heating block. And from with the help of this gear, the material will come into the material melting heating block. And from the material melting heating block, the solid wire formed material will convert into liquid form, and the melted material is deposited in layers, and we will get the final 3D printed part. Yeah, again, this is another image representing the working of fused deposition modeling. Here, this is the heated extruder. Material will enter into the heated extruder, and we will get the final 3D printed part like this. So here in the image, we can see the object is formed with the n number of layers. So that's why this is called a layered manufacturing, or layer by layer manufacturing, or layer based manufacturing. There are so many names: layered manufacturing, layer by layer manufacturing, layer oriented manufacturing, because we are adding layers, different layers, so that we will get the final part. And this one, yeah, this is a very simple figure representing the working of fused deposition modeling. So this is my material, polymer or any other material, and this will enter into the pinch roller mechanism. And from the pinch roller mechanism, it will enter into the liquefier. And inside the liquefier, this will convert into liquid form. And through the small orifice, through the nozzle, we will get the liquid form of the material, and this material will add on the platform so that we will get the final 3D printed part. Yeah, this is again another figure representing the working of fused deposition modeling. This color represents the material, and these two circles are called pinch roller mechanism. And from this pinch roller mechanism, this will enter into the heater or liquefier. So inside the liquefier, that will convert into liquid form, and at the end of the liquefier, there is a small diameter orifice will be there. Through that orifice, we will get the layer, so that the extruder will add each layer, and finally we will get the 3D printed part. So this is the basic working behind the 3D printing, fused deposition 3D printing technology. So in the Google, we can see so many n number of images representing the working of fused deposition modeling. You can take any one image so that you will get a better understanding about fused deposition modeling. So fused deposition modeling is also known as fused filament fabrication. It is a widely used method in the field of 3D printing technology. In fused deposition modeling, a continuous filament of thermoplastic material is heated and extruded through a nozzle which moves along both horizontal and vertical axes to deposit material in layers building a three-dimensional object. The key components involved in FDM printing include the feeding mechanism, which guides the filament into the printer, the pinch roller mechanism. This circle, this represents the pinch roller mechanism, which ensures proper filament feeding, the power supply, and the liquefier dynamics, which control the melting and extrusion of the filament. In wire additive manufacturing, also known as wire 3D printing, a diverse range of materials can be utilized in the form of wires, including polymer composites, wax, and various metals. The material flow can be precisely controlled, allowing for either continuous deposition or on-demand drop-by-drop material placement. So here in this FDM, the material flow is continuous. So there are two options: continuous deposition on demand or drop by drop material placement. So I already explained one 3D printer called Arberg that supports the drop by drop material placement. So please check in the Google the 3D printer named Arberg that supports the drop by drop material placement. So providing flexibility in the fabrication process. The machines employed in wire additive manufacturing can be characterized by their kinematic configurations, which may include serial, parallel, or hybrid systems, each with its own implications for precision, speed, and versatility in manufacturing complex geometries. The energy sources used to melt the wire for deposition are crucial to the process and can involve various methods such as resistance heating, induction heating, arc welding, and advanced energy beams like laser or electron beams. The choice of energy source can impact the quality, speed, and material compatibility of the additive manufacturing process. Moreover, the support mechanism in wire additive manufacturing is an essential consideration as it directly impacts the fabrication of intricate structures. Support mechanisms can include water-soluble supports which dissolve after the printing process, acid bath supports, or multi-axis kinematics that eliminate the need for additional support altogether. Each support method has distinct advantages and limitations, influencing the manufacturability of complex, overhanging, or intricate designs. Wire additive manufacturing is a process whereby materials are added layer by layer to form a three-dimensional object. This process involves the use of materials such as polymers, composites, wax, or metal. So this material can be either polymer, composites, wax, or metals, which are fed into the machine in the form of wire. The material flow can be either continuous or on demand, which means that the material is either fed continuously or in small drops as required. The machine kinematics used in wire additive manufacturing can be serial, parallel, or a hybrid of both. In serial kinematics, the additive manufacturing process is carried out in a linear fashion, with the wire being fed into the machine from one end and the finished product emerging from the other end. In parallel kinematics, the process is carried out in a more complex manner, with the wire being fed into the machine from multiple angles and the finished product being built up from multiple layers. The energy sources we are using in wired manufacturing include resistance heating, induction heating, arc melting, or energy beams such as laser or electron beams. Resistance heating involves passing an electric current through the wire, which heats up and melts the material as it is fed into the machine. Induction heating involves using a magnetic field to heat up the wire, while arc melting involves using an electric arc to melt the wire. Energy beams, such as either laser beam or electron beams, use a concentrated beam of energy to melt the wire and form the finished product. Overall, wire additive manufacturing is a versatile and flexible process that can be used to create wide range of objects from simple shapes to complex geometries. The choice of material, machine kinematics, and energy source depends on the specific requirements of the project and the desired outcome. Then coming to the company named Stratasys. So Stratasys is a 3D printing company. It's an American Israeli manufacturer of 3D printers, software and materials for polymer additive manufacturing as well as 3D printed parts on demand. So I'm clicking the website of Stratasys. Yeah, this is the website of Stratasys. If you want more details, you can click this website so that you can see the different types of 3D printers such as FDM supported 3D printers using polyjet technology, P3 technology, soft technology, stereolithography technology, etc. So you can, if you want to see FDM printers, so click here. You can see these are the FDM printers. So the FDM printers currently available under Stratasys are F3300 industrial 3D printer, Fortress 450 MC, F900, F123 CR series, F370, F770, and F170. So these are the FDM 3D printers available under the Stratasys company. So who is Stratasys? So Stratasys Limited is a renowned and innovative manufacturer of cutting-edge 3D printing technology. The company offers a wide range of products and services, including 3D printers, softwares, and materials for polymer additive manufacturing. Stratasys also provide on-demand 3D printed parts, making it a one-stop shop for all 3D printing needs. Founded in Israel in 1989, Stratasys has grown into a global company with a presence in the United States and around the world. The company has enjoyed significant success in the 3D printing market because of its quality, innovation, and customer satisfaction. Stratasys 3D printers are designed to handle a variety of applications from rapid prototyping to production grade manufacturing. The company's software solutions enable users to design, simulate, and optimize their 3D models, while its materials portfolio includes a range of thermoplastics, photopolymers, and other materials to suit different applications. In addition to its hardware, software, and materials offerings, Stratasys also provides a range of support services including training, consulting, and technical support. With its comprehensive suite of products and services, Stratasys is a leader in the fast-growing and dynamic world of 3D printing. So next is we will explain the the basic working of fused deposition modeling. So as we all know, fused deposition modeling is a widely used 3D printing technique that involves a few important steps. The process starts with the pre-processing, which is the first step. In this step, a computer-aided design CAD model is created, and then it is converted to an STL format, standard tessellation language file. The STL file is then oriented and support structures are generated. This is done to ensure that the final product is stable and has a proper structure. The model is then sliced into layers and the area is filled. Finally, G codes, which are instructions for the 3D printer, are generated. The second step in FDM is building the part. After pre-processing, the second step is the building process or building the part. This step involves depositing buffer layers, which are used to ensure that the part adheres to the build plate. After that, the main material is deposited layer by layer. This process continues until the part is complete. Depending on the complexity of the part, support material may also be deposited. This is done to ensure that overhangs and other complex features are properly supported during the printing process. The final step and the third step is called a post-processing. This step involves removing the support structures from the final product. This can be done manually or with the help of a support removal system. Once the support structures are removed, the surface of the part is finished. This can be done with sanding, polishing, or other techniques to achieve the desired surface finish. So fused deposition modeling is a sophisticated 3D printing technique that involves several important steps. By following each step carefully, one can produce high quality parts with a wide range of applications. Then next is called during the post processing, we have to remove the support structure. So one example is called Stratasys waterworks. Yeah, here you can see waterworks concentrate. This is a with this waterworks concentrate, we can deposit our final fabricated part into the water consisting of this concentrate. The support structure will automatically remove from the part. So that is the use of this Stratasys waterworks. It is a soluble concentrate. It's a specified solution that comes in a case of 12 units. It is specifically formulated to effectively dissolve the soluble support material used in FDM builds from Stratasys printers, ensuring efficient and precise post-processing of 3D printed objects. So when you deposit your final part with the support structures into this solution, after some time, the support structure will automatically remove from the final 3D printed part so that we will get a finished, a precise, efficient final part after the post-processing operation. So there are, as I already mentioned, there are different 3D printers uh, uh, manufacturing by the company named Stratasys. So the different FDM 3D printers are F3300, Fortress 450 MC, F900, F123 CR series, F370 series, F770 series, and finally F170 series. So we will see something about F3300. So this F3300 introduces a new standard in FDM industrial 3D printing, offering up to twice the speed and throughput of standard fused deposition modeling 3D printers. Designed for manufacturing, the F3300 enhances productivity, print reliability, and part yield with advanced hardware and software technology. These capabilities efficiently address numerous applications in industries such as automotive, aerospace, rail, general manufacturing, and medical. The industrial FDM printer is equipped with advanced technology to meet today's manufacturing challenges. It reduces the overall cost per part through faster print speed, more efficient material cost, and increased part yield. By printing it up to twice the rate of other extrusion 3D printing systems, it increases throughput. Additionally, the printer boosts print reliability to enhance part yield and ensure predictable performance in a production environment. Its ease of use, including auto calibration, reduces 3D printing labor by eliminating time-intensive manual calibration. The F3300 revolutionizes FDM technology with new features that enhance productivity while lowering cost and labor. Faster gantry speeds enable faster point-to-point material deposition for quicker print speeds and reduced time to part. Multiple extruders provide redundancy for higher reliability and eliminate non-print time typical with single extruder thermal cycling. The auto calibration feature eliminates the time previously needed for manual calibration after a material change. Multi-resolution printing uses small and large bead thickness in the same print job to expedite the time required to complete the part. Faster extrusion rates enabled by new extruder technology contribute to faster print speeds and greater throughput. Another printer, the second printer is Fortress 450 MC. This image, this is called a Fortress 450 MC. So it offers the advantages of industrial FDM additive manufacturing, including speed, cost savings, and material options. It is a reliable 3D printing solution trusted by manufacturers in aerospace, automotive, rail, oil and gas, medical and commercial products industries. When used with an open AM material license and associated software, the Fortress 450 becomes an open system allowing users to edit print parameters for optimal material performance. Additionally, validated materials such as Victrex AM200 are available to expand the printer's material selection, increasing material availability and widening the scope of applications. Victrex AM200 is based on LMPAC technology and is part of the PEAK family in the PEAK polymer group. Then the next printer is called a F900. The third printer is called a F900. So this image is representing Stratasys F900. So it produces highly accurate 3D printed parts with repeatable, reliable performance using the Stratasys F900, the workhouse of industrial FDM 3D printing. Manufacturing leaders from every industry trust the F900 for its consistent uptime, dependable output, and data security. Along with our Industry 4.0 software solutions, the F900 is unmatched in industrial 3D printing. The F900 boasts the largest build chamber of any Stratasys FDM printer, providing the space needed to print large parts or multiples of smaller parts in a single build operation. Additionally, with the largest selection of polymer materials available among Stratasys FDM printers, the F900 can execute virtually any 3D printing application in industries spanning aerospace, automotive, rail, medical, and general manufacturing. Then the next machine is called F123CR series. Yeah, this image is representing the printer named F123CR series. So we can enhance the machining capabilities with the cutting edge technology of carbon fiber 3D printing, that is called a CR, carbon fiber 3D printing. The F123CR series composite 3D printers are equipped with advanced carbon fiber and industrial grade thermoplastics, allowing for the production of robust work holding fixtures, tooling, and parts. Consisting of the F190CR and F370CR systems, the composite ready printer family delivers dependable 3D printing solutions tailored to meet the rigorous demands of various industries such as general manufacturing, automotive, aerospace, rail, education, and medical. Then the next 3D printer named F370 after F123CR series. Next is the F370. Yeah. So 3D printers revolutionize the way engineers and designers approach prototyping and production. The F370 is a cutting-edge example of this technology, offering a seamless CAD to print process facilitated by GrabCAD print software. This ensures that users can effortlessly bring their designs to life with a minimal hassle. In addition to its user-friendly interface, the printer boasts an impressive array of materials, including carbon fiber, thermoplastic polyurethane, and other high-grade thermoplastics. This diverse selection empowers creators to produce parts with a wide range of characteristics catering to various industry needs. The printer facilitates swift material changes, features a spacious build volume, and consistently delivers precise and reliable print results. So these capabilities make the F370 a versatile tool for both office and manufacturing environments. And the last FDM printer, that is the not last, F770, one more is there. Yeah, F770. Yeah, this image is representing the F770 3D printer. So this F770 FDM 3D printer stands out for its impressive print volume, offering over 13 cubic feet of build volume and the widest build chamber among all Stratasys FDM systems. This means that the F770 is capable of producing large individual parts or substantial assortments of smaller parts in a single build. By eliminating the need to print separate sections of a large part and join them together post-print, the F770 ensures that big parts can be produced in their entirety with the exceptional reliability and repeatability that Stratasys FDM printers are renowned for. Leveraging the substantial capacity of the F770, businesses can efficiently address diverse applications in automotive, general manufacturing, aerospace, education, rail, and medical sectors. And the last printer that supports FDM technology is F170. So this F170 provides educators, engineers, and designers with cost-effective access to high-quality 3D printing. Its design focuses on simplicity, starting with a seamless CAD to print process facilitated by GrabCAD print software. This printer offers a wide range of materials, including carbon fiber, thermoplastic polyurethane, and other advanced thermoplastics. With its quick and effortless material swaps, large build volume, and consistent print quality, it enables precise and reliable 3D printing for educational and professional settings. So if you want more details about the FDM printers, polyjet stereolithography, P3/DLP, digital light processing, SAF or powder bed fusion, so you can refer this website. Next is the machine architecture of the FDM 3D printing technology. As I already mentioned, in fused deposition modeling, the feedstock used is typically an amorphous thermoplastic polymer filament, which typically has a diameter of 1.5 mm to 3 mm. In smaller scale systems, the feedstock is simply a loose coil, while larger manufacturing systems use a cartridge to supply the system. The filament is pushed through a pinch roller mechanism. Here you can see two circles. These two circles are called a pinch roller mechanism, and this is connected to a stepper motor. The stepper motor provides the energy to move the filament through the system. The rollers are made of hypalon or polyurethane, and one or both of them have a grooved or toothed surface to create sufficient friction to grab the filament and feed it into the liquefier without slippage. The pressure on the filament between the rollers is typically enough to slightly deform the filament, leaving small tooth marks so as to avoid crushing the filament. This is important because if the filament is crushed, it can cause inconsistent extrusion, which can result in a poor quality print. So the pinch roller mechanism is an essential component of FDM 3D printing, as it ensures that the filament is fed smoothly into the system, allowing for consistent and high quality prints. The pressure on the filament between the rollers is typically enough to slightly deform the filament, leaving small tooth marks so as to avoid crushing the filament. This is important because if the filament is crushed, it can cause inconsistent extrusion, which can result in a poor quality print. So the pinch roller mechanism is a very essential and important component in FDM 3D printing so that it allowing for consistent and high quality prints. So the pinch roller mechanism is a critical component in FDM 3D printing that assists in feeding the material into the liquefier. Yeah. The material is placed above the pinch roller where it experiences tension, while below the roller it experiences compression. So above this roller, this raw material undergoes tension, while below the pinch roller mechanism it experiences compression. This mechanism ensures a constant and uninterrupted supply of material into the nozzle. To understand the pinch roller mechanism's function, it is essential to know how it works. The pinch roller is responsible for guiding the filament into the liquefier where it is melted and extruded. The filament moves through the pinch roller and into the liquefier through a small orifice. The angular velocity of the pinch roller plays a crucial role in determining the filament's feed rate into the liquefier. This velocity can be calculated using the formula omega r is equal to 8 kf into Vt into Wt divided by pi into dr df square, where W and T, we are assuming the shape of the layer is a rectangle so that the area, that means the width into thickness, that is W into T. And Vt is the transverse velocity, dr is the diameter of the pinch roller, and df is the diameter of the filament. And kf is called a friction factor. And there are three cases for kf. If kf is equal to 1, that is called ideal gripping and feeding. If kf is greater than 1, then the filament is crushed by rollers. And if kf is less than 1, then the filament slips between the rollers. So kf is called a friction factor. So with the help of this omega r, we can calculate the angular velocity of the roller or pinch roller mechanism. That is equal to 8 into kf into Vt into Wt, the whole divided by pi into dr df square. Proper calculation of the angular velocity ensures that the filament is fed at the appropriate rate, ensuring optimal printing conditions. So the pinch roller mechanism is a very critical component in FDM 3D printing that ensures a consistent and uninterrupted supply of material into the liquefier, resulting in high quality prints. The liquefier. So below the pinch roller mechanism, we can see the liquefier. So the liquefier dynamics is very important. The liquefier is, this is also known as print head. This also plays a crucial role in the 3D printing process. And this area is responsible for melting the solid polymer feedstock and then pushing it through a small print nozzle. The dynamics of the liquefier are highly intricate and pose a significant challenge when it comes to modeling, primarily due to the fact that the melt properties exhibit nonlinear behavior in response to changes in temperature and shear rate. The force needed to push out the melted material must be strong enough to overcome the pressure difference throughout the system. This depends on the thickness of the melt and the design of the heating and nozzle systems. Because the melted material sticks to the heating and nozzle surfaces, it undergoes shear deformation as it flows. Thermoplastic materials used in FDM currently show shear thinning behavior, meaning that their viscosity decreases as the shear rate increases. For modeling FDM melts, it is reasonable to use a power law for generalized Newtonian fluids to represent polymers like ABS. So I'm concluding this session. So in this video, we learned the fascinating world of wire additive manufacturing, exploring its various classifications and options. We also took a closer look at the innovative 3D printers offered by Stratasys, such as F3300, Fortus 450MC, F900, F123 CR series, F370, F770, and F170, uncovering the intricate details of their functionality. So we also examine the intricate steps involved in fused deposition modeling, including the intriguing process of support structure removal using waterworks. Also, we learned the feeding mechanism and a pinch roller mechanism, and also calculate the angular velocity of the roller. And also we learned the complex dynamics of liquefaction and melt properties. So with this, I'm ending my session. If you want to learn more about the Stratasys FDM, you can visit this site so that you can explore more details about the different FDM 3D printers and their working. Thank you.